ঠিক আছে okay we started the recording today's class the distance between the question says that what is the current wavelength. Now what we need to see is that this person is moving this rope up and down and the wave is traveling in this rope medium and it is getting reflected off the wall and bouncing back. This solid line is the position of the rope at a certain point in time, and this dotted line represents the rope position in another time. So these two things does not mean two different ropes being rotated. So this is one position, this is another position. Now simply what I need you to observe is that if you simply what I need you to observe is that here I need you to see that how much আচ্ছা মিথিলা হ্যাঁ প্রবলেমগুলো রাখো আমি নিচ্ছি পাবলিকে দাও বাবা প্রবলেম লিস্টটা পাবলিক ছেড়ে দাও তাহলে সবাই দেখতে পাবে যে কি কি প্রবলেম নিয়ে আলাপ করব so what I need to observe is that if I just draw a straight line over here just to get an idea of the equilibrium, you'll see that I can draw over here a straight line to represent the equilibrium. Now we can very easily you can see that this much shows you one wavelength and this much shows you the other wavelength. Can you see that? How many complete wavelengths are here? Two. Not four. Have a look. If you have an equilibrium line drawn, this much is one full wavelength, or this much is one full wavelength, or you can say this much is one full wavelength, crest to crest, or you can say this much is one full wavelength. These are the four distinguishing parts of wavelengths that you have to know. All of these, the lengths represent one full wavelength. So this much and this much, one top, one crest, and one trough together makes one wavelength. So you can see over here that from here to here, do you see the entire shape of the curve? No, you're seeing half of this curve. So you're seeing, let's say, this part over here, and then you are seeing the top part. So you're seeing the crest half over here. So together from here to here, you get one wavelength, and from here to here, you get another wavelength. Have a look. This is not four wavelengths. This is two wavelengths, 2 lambda. Can we agree on that?
Yes, sir.
Okay. So this is 2 lambda. So which means currently the wavelength is supposed to be 1 meter. So that is wavelength shown হচ্ছে 1 meter. তার মানে B আর A বাদ, the possible answers are C and D. Okay. The next thing that we have to consider that as long as the medium is kept constant, kept constant in the equation B equals to F lambda, V will remain a constant. For a fixed medium, for a fixed type of wave, V is ideally a constant. If you wonder the word, why am I using the word ideally? Because V can be changed for the same type of wave for a lot of different factors. For example, if you consider the speed of sound through air, humidity, temperature, this also change the medium property of the air for which the speed of sound through air can be varied. So, but as long as you compare two sound waves in the same identical air, same humidity and same temperature and everything, then you can say for no matter what is the frequency of the sound wave is, both the sound waves, as long as they are sound waves traveling through the same identical air medium, they would have the same speed. So rule of thumb, what you can remember and should remember that if medium is unchanged or medium is there is no difference between the medium, then same type of wave should have same speed through that medium. That's why I'm showing over here the speed V in a rectangle, representing that it is a constant. So if this is a constant, it means what? F and lambda should be inversely proportional, because the product of these two things should be equals to a fixed value, which means if lambda goes higher, then F goes lower and vice versa. Now the question says, and what will be the wavelength when the student doubles the frequency at which the free end is moved up and down? If F is doubled, increased by a factor of 2, then lambda should become reduced by a factor of 2. So initial wavelength was 1 meter, new wavelength should be half meter. So D is the correct response. Check this out.
Yes, sir.
ঠিক আছে?
Yes, sir.
হ্যাঁ বলো এরপর পেজ নাম্বার 3 তে কোনো প্রবলেম? সবাই একটু রেসপন্ড করো যারা লিস্টে প্রবলেম দিছো। I appreciate this. Still, when I'm in the page that you ask me problems by, respond. Page number 3 তে কার কোনো প্রবলেম?
Sir, 13
দেখবো। 13 আইডিটা খুব সিম্পল. I'll take this picture. I'll help. Have a look at 13. The dependent ripple tank vibrates at a frequency of 4 Hz and the resulting wave pattern is photographed. The distance between the two crests shown is 20 centimeter. So the two crests which are labeled over here, that much gap is 20 centimeter. What is the speed of the wave? This is a very pretty simple problem. Have a look. What I need you to understand that each of these curved lines represent one wavefront. And from one wavefront to the next wavefront, the amount of space that we have is named as 1 lambda. Because this is the crest of one set of waves, this is the crest of the next set of waves, the very next set of waves. So crest to crest gap is 1 lambda. So all that you need to count is that how many lambdas are between this wavefront and that wavefront. So you just count how many gaps. 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda. So in this case, 5 lambda equals to 20 centimeter. Therefore, lambda equals to how much? 4 centimeter. See if it makes sense.
Yes, sir.
Yes, sir. So once you have this, then the rest of the part is pretty simple. V equals to F lambda. V equals to F lambda মানে হচ্ছে V equals to F lambda হচ্ছে for F হচ্ছে 4 Hz and lambda is 4, so 4 4 is 16 centimeters per second. C is the correct response. হ্যাঁ বলো।
এখানে the distance between the two crests বলা আছে।
বুঝি না বলো।
এখানে বলা আছে distance between the two crests.
As shown in the figure. As shown.
এখানে না ল্যামডা তো 5টা তাহলে দুইটা ক্রেস্ট হলো কেন?
Oh, acha. If I try to show you the side view of the medium for this much part of the medium, let's say if I try to show you the side view of this part of the medium, this side view might as well look like this. For that instance, so you are label 1 2 3 4 আরটা লাগবে। You are given the labeling of the lambdas from here through here. বুঝে গেছ পারছি?
Yes sir.
মানে এখন ক্লিয়ার হইছে?
Yes sir.
আচ্ছা বিউটিফুল। মুনাম বুঝছো?
জি স্যার।
আচ্ছা অবশ্য। 14 what is meant by the term wavefront? না 14 না সরি বলো আর কোন প্রবলেম এই পেজে আর কোন প্রবলেম পেজ নাম্বার 3 তে anything else from page number 3?
স্যার 15
The diagram shows the ball floating in a tank of water. Which diagram shows the movement of the ball as the wave passes? Water waves are transverse waves. So the water particle will move equal distance perpendicular to the direction of the vibration up and down. So have a look, where do you have this thing? The wave is coming by, water ball was initially stationary. As the wave is going to pass through the ball location, it's going to move perpendicular to the direction of the wave. So this is the direction of the wave, perpendicular one হচ্ছে vertical, which is up and down. And that movement should have equal amplitude on both sides on the equilibrium. Equilibrium উপরে যতটুকু উঠবে নিচে ততটুকুই নামবে. So that's why the correct response is only D. বুঝতে পারছি?
জি স্যার।
আচ্ছা
স্যার
এরপর পেজ নাম্বার 4 এ কোনো প্রবলেম?
স্যার
বলো
স্যার নাম্বার 2
স্যার এই যে 14 এর যে এ যেটা ছিল
জি
ওটা জানি কি ওয়েভ
14 এর A
ওয়েভলেন্থ স্যার হ্যাঁ থ্যাংক ইউ
the gap between two successive wavefront is wavelength.
ঠিক আছে থ্যাংক ইউ
আচ্ছা আচ্ছা 9.2 দেখবো।
নাম্বার 2
Number 12 help. Number 2 says a sound wave is reflected from a brick wall. Compared with the incident wave, the reflected wave has what? Well, what I need to understand is that in the process of reflection, the waves are bounced off a boundary and it simply changes direction, but it remains in the same medium. Here, it was a sound wave in air medium. After the reflection, it is still within air medium. Check this out.
Yes sir, understood.
Yes, sir. So the only thing that you are having changed is direction. That's one factor. Now, additional to the direction factor, you can also consider there is another logical change, that is the energy amount of the wave, which might not be a part of the MCQ on this part, because we have what? We have good answer. I mean, the part that I'm trying to explain is, let me go through that, is that whenever a certain wave falls onto the boundary of another medium and bounced off, or that is reflected off that medium's of the second medium's boundary, certain portion of the wave's energy is absorbed by that reflection surface. So if this, let's say if this wave is coming down here, containing an energy of, let's say, 100 unit. What is that unit? I'm not telling you, so that you don't get bothered by it. Let's say this wave by some measurement contains an energy of 100 unit. After the reflection, this wave would have definitely some less amount of energy than 100, because this surface would absorb a significant portion, not negligible, significant portion of the energy within itself in the process of reflection. So you can say that the new sound wave is going to become less volume. It's the reflections are gonna be heard to be less louder compared to the thing. So in this case, the correct response is C. C. The reflected wave has the same.
Direction change হলে তো velocity change হয়, তাহলে same speed হবে না?
I think C is the correct response. Masim দেখো তো এটা correct response কি?
C.
যদি এখানে lower amplitude থাকতো তাহলে কি সেটা correct answer হতো given your explanation?
লোয়ার অ্যাম্পলিটিউড তাহলে সেটা কারেক্ট আনসার হওয়া উচিত ছিল, যে কারণে ওরা লোয়ার অ্যাম্পলিটিউড দেয় নাই। তোমাদেরকে ওরকম পারপ্লেক্সিং এমসিকিউ দিবে না, বাই অল মিনস দ্যাট আই হ্যাভ কাম অ্যাক্রস মাই এক্সপেরিয়েন্স। লোয়ার অ্যাম্পলিটিউড দিলে সেটা হতে পারতো। শর্টার ওয়েভলেন্থ বা লঙ্গার ওয়েভলেন্থ কোনোদিনই হবে না। দিস ইজ নট utterly unacceptable because there is no medium change, so there is no possibility for wavelength variation. Same velocity হবে না because the duration is getting changed, so the velocity is essentially not the same. This is the correct response for this option, and if this was a smaller amplitude, then this would have been something else, so that you wouldn't have to choose this one. Then you could have chosen a smaller amplitude or a smaller loudness. That would be also acceptable.
So if the energy is lost to the surroundings, won't the speed decrease?
The speed is not a dependent factor on the energy content. The speed of a wave is a default factor on the medium and the type of the wave. If I put it in this way, let's say, let me put it this way, let's say,
আপনি medium বলেছেন না, তারপর
type of wave.
wave and medium. Okay, sir.
How can I put this example down? Amount of energy is basically a content of how much frequency and amplitude that you have. I mean, both of these factors, both of these factors have some contribution towards the content of the energy within a wave. But speed of a wave does not essentially. Speed of a wave is not dependent on the energy. What I need to understand, kids, try to get this. Speed of a wave means how fast the vibration passes through the medium. It doesn't have anything to do how fast the medium particles oscillate about their equilibrium position. So what is the speed for the energy to transfer from one particle to the next particle, and also how far they are apart? These two factors determine the speed of the wave, how fast it is progressing through the medium. That has almost nothing to do exclusively with the rate of vibration. So Hassan je question shows that more energetic wave should be faster wave. No, that's not essentially true.
এটা হতে পারে না যে a large amount of energy it is very possible for it to be traveled in a low wave speed and a low amount of energy to be traveled in a high wave speed given appropriate situations.
If you say given appropriate situation, then that should not be a general rule of thumb. That can be constructed because we want it to happen. But whether that should happen almost always naturally, that cannot be predicted.
Okay, sir.
We can make it to happen like that, but we cannot be sure that this will be the case always.
কোন ফ্যাক্টরের সাথে এনার্জি রিলেটেড ওয়েভ অ্যামপ্লিটিউড আর আরেকটা ফ্যাক্টর কি ছিল?
You don't need it for your syllabus, but since you are asking amplitude, frequency, and also I goes to 2 pi f square a square. Yeah, these are the two factors.
Amplitude and frequency as well.
That's what the mathematical equation goes by, but you don't have this thing information in your syllabus anyway. Anything else from this page? Anyone?
টুটা বুঝতেছি না।
এতক্ষণ আমরা 2 আলাপ করলাম, বলো কোন পার্টটা বুঝো নাই?
মানে এটা শর্টার ওয়েভলেন্থ কেন হবে না এটা?
Whenever the wave change direction, did it undergo any refraction or is there any medium change?
No.
Then the speed is constant.
Yes.
And the frequency is exclusively dependent on the source, which I told you earlier. Frequency is exclusively dependent on the source. After a wave has been produced from a source, no physical phenomenon, reflection, refraction, radiation, or whatever, nothing will change the frequency. So your speed is a fixed thing, f is a fixed thing, so your lambda has to be same as well.
Yes.
So you cannot have a shorter wavelength, neither can you have a longer wavelength. The reflected wave should have the same equal wavelength as the incident wave. That's why B is not a correct answer.
Sir, এটা কি ইকুয়েশন থেকে ডিরাইভ করছি নাকি there is a proof to it as well?
You don't have to know the proof. You don't have to know how to prove it. You just have to know this information is correct. But I essentially derived it from the. I mean, if I have to explain how can you say that there will be a short. I mean, B is the wrong answer. I will definitely go by explaining that question. Explaining that question for the answer using the equation V equals to F lambda. That I'll always do. If this ever shows up in a structured question paper too. Munayan, further question bolo. আর কোথাও কনফিউশন আছে বলো।
আর নাই স্যার এটাই।
All right, anything else from this page? Anyone? No. Acha. Page number 5. Reflection 9.3, page number 5 থেকে কোনো problem? There are a lot of repeated problems over here. Many of the problems have the same working principle. So if you are able to do one thing properly, you might as well be able to do all the rest of the parts easily as well. Yes? No?
Number 3.
Number 3. Okay, well, we'll have a look. Number 3 says the waves pass from deep water to shallow water and reflection occurs. What is the speed of the wave in the shallow water? Okay, we have in the deeper water the wavelength is 1 meter and the speed of the wave is 2 meters per second. In the shallow water the wavelength is 0.4 meter and we want to calculate how much is the new speed. So if you can see very easily go for the equation that V equals to F lambda, but for this case F is a constant, right? Sorry. For this case, F is a constant. So I can very well write that V1 equals to F into lambda 1 and also V2 equals to F into lambda 2. I can write this because F will be constant for both of them before refraction, after refraction. If you divide these two equations, then you're going to get what? V1 by V2 equals to lambda 1 by lambda 2. So using this process, you can calculate the new lambda by a single equation. You don't have to calculate the frequency. That's one way to do this. Or alternately, you can do this for the incident wave. You can use this exclusive equation, calculate the value of the frequency, then use the frequency value in this equation to calculate the new speed. So you can also do two set of calculations, finding out the frequency itself. Both of the workings are perfectly equal, perfectly acceptable because it's an MCQ question. Make sense?
Yes, sir.
Sure. Anything else from these pages? Anyone? Page number 6. Page number 6. 12 বুঝছো সবাই?
Sir, 12 a problem.
12 I hope. 12 দেখো. A set of straight water ripples in a ripple tank travels over a thick triangular perspex sheet. Which diagram shows the wave pattern? এই ফার্স্ট সেন্টেন্সটা খুব ভালো করে খেয়াল করো। Take a good look at the first sentence to make sense out of it. We have a triangular perspex sheet that is submerged under the water. So which means above that triangular sheet, the water medium is shallow. Everywhere else, the water medium has the same depth, which means you can think in terms of the property of the wave. Everywhere else, it's the same water medium. Exclusively above the perspex sheet, the water medium is shallow. So in the shallow medium, the wave is going to become slower. So the wavelength should decrease. And that should only happen above the triangular perspex sheet region. Now in A, you can see that they are showing you some refraction, but they are making the refraction happening in this region as well. In this case, you are not supposed to have refraction because the depth of water medium before this, here and here, everywhere, other than above the triangular perspex sheet, everywhere the water medium has the same depth. Can you all agree on this information?
Yes, sir.
Okay, so this one is unacceptable because this is showing refraction in an unacceptable place. Same thing over here. Now here comes C and D. Now, what I need you to understand that above the perspective shift, the depth of the water is shallow, which means the wave is going to become slowed down. Slow down means the wavelength is going to become smaller. All right. So the gap between the waves are going to become less. So which one of these two answers represent a reduction of wavelength?
C.
Do you see it? Which one of these two options represent reduction of wavelength? It has to be C. You can see it very well. Or if you are confused, you can use your ruler and press your ruler against this thing. You'll see that this much gap is bigger and each of these gaps are smaller. You can actually calculate this out. So C is the correct response for the actual figure. I'll do a bit of additional discussion about option choice D, but before I do that, I need everyone to comply that you did understand this part of the discussion. Mamun, everyone, please comply.
Okay, sir. বুঝছি.
Yes, sir.
Acha, can anybody try and have a guess? How could we possibly make the shape of D? How could we possibly make the shape of D?
By making it less denser.
How can you possibly change physically? I mean, what you said is theoretically correct. Okay, but what change should you bring to the ripple tank setup to obtain a reflection behavior like that?
Sir, আমরা যেটা করতে পারি triangular perspex কে আরো deep করে দিতে পারি না than the rest of the region. That makes it much more deep. Therefore,
what do you mean by making it deeper? The triangular perspex sheet is triangular perspex sheet.
এই যে এটা যেখানে আছে the rest of the water medium is above.
স্যার গ্লাসটাকে একটা মোটা করে দিব ঠিক আছে তো?
Well, that
Sheet,
would make the water even shallower. Afardin.
ও সরি চিকন করে দিব।
Then if you even Sabir, আমি আসছি তোমার কোশ্চেন আসতেছি, if you even make the glass sheet a little thinner, then also above the above the triangular perspex you will have shallower water, less shallower water than the other places, but in this case you will still have shallower water compared to the other parts.
Sir, এই যে আমি যেটা বলতে চাইছিলাম যে ওই triangular অংশটা আছে না, we get a custom made triple tank which has that triangular region deeper than the rest of the region, increasing the wavelength as there is less resistance against the flow of the energy and therefore larger.
Okay, how could you possibly make that design? I totally get your point, Sabi. What you have said is absolutely correct, but can you give me a physical way to achieve that?
Sir,
by using a glass on the other side of the what is this ripple tank, but keep that triangular region normal. Like it's like cutting out the triangular shape and putting it into the ripple tank, making the rest of the region shallower.
That is exactly what I was looking for. Yes, Obi Bolo.
Sir, triangle-টা মানে যেখান থেকে নেওয়া হয়েছিল ওটার inverse area-টা cover করব perspective.
That is exactly what I was trying to go for. Let's say you have cut off the triangular perspex sheet from a piece of rectangular piece. Now what you need to do, take out this triangular perspex sheet out of the water and bring about that remaining piece of the perspex and put it under the water, so that now everywhere else you will have less depth and at this region you'll have deeper. So this would be the shallower medium, this would be the deeper medium. So inside the deeper medium you're going to have increase of wavelength. That you can do. That's what's going to give you shape number D. See if every one of you can understand.
Sir, একটা প্রশ্ন ছিল।
Follow.
Sir, the speed does not depend on the energy of the wave, but the increased resistance against the flow of the energy of the wave decreases the speed. এই অংশটা ক্লাস ওভারে আমার কনফিউশন হচ্ছে।
আমি বুঝি নাই, আবার বলো।
Sir, আপনি বলেছিলেন that the speed of the wave is unrelated to the energy of the wave, right?
Yes.
So এখানে increased resistance against the flow of energy is making the wave slower or faster or vice versa. So এটা একটু ক্লাস ওভার হয়ে গেল না?
So it is actually about how fast or it is about how much the medium particles themselves are willing to vibrate or unwilling to vibrate. That is not directly related to the absolute amount of energy content in the wave. A deeper medium wave particle, water medium particles, you can pretty much visualize it that they are willing to make bigger amplitudes. A shallower medium water particles are willing to make amplitude, sorry, ভুল বলছি, they are willing to make bigger wavelengths, but the water particles within a shallower medium are willing to make a smaller wavelength. That does not necessarily mean that how much medium particle are you gonna vibrate, because I did not teach you this, that how the energy content of the wave could possibly affect the wavelength, because it actually doesn't. Directly it doesn't.
ওকে, আমাদের লেকচার কপিতে এই ডেফিনেশন দেওয়া ছিল, তো তাই আমার এই যে কনফিউশনটা ছিল।
Okay, you snap a picture of it and send it over to our messenger window, because that's easier to share pictures. I will talk about this, no problem.
ওকে স্যার,
Sure.
Thanks.
No problem. Page number 7. EM spectrum usage. EM spectrum uses এর জন্য তোমাদেরকে আমি ক্লাস নোটস এর লাস্ট একটা পেপার দিয়েছিলাম, ওটাকে আমি তোমাদের আলাপ করছিলাম। Did I discuss that paper? নোটস এর লাস্ট একটা জিনিস ছিল যে you guys might ask what notes এর শেষে কি ছিল, what কি?
স্যার এই যে ইলেকট্রোমোটিভ কি জানি,
এই জিনিসটা কেউ দেখছো উল্টা, এই যে এখানে যেটা জিনিস আছে, did any of you come across up to this part of your paper to worksheet?
yes sir.
Acha, for those of you who have not come across this one, read these parts. I'm having this open for all of you. I need you to read this part right now.
এটা কই?
এটা হচ্ছে পেপার 2 ওয়ার্কশিটের একদম লাস্টে শেষে, পেপার 2 ওয়ার্কশিটের একদম শেষে, পেপার 2 ওয়ার্কশিটের একদম লাস্টের দিকে আমি ইউজেস অফ EM স্পেকট্রামের একটা ছোটখাটো একটা নোটস দিচ্ছি এখানে, প্লাস একদম শেষে আমাদের রিপোর্ট ট্যাঙ্কের একটা ফিগারও দেওয়া আছে ফর ইওর রেফারেন্স। রিপোর্ট ট্যাঙ্কের একটা সিম্পলিফাইড ফিগারও দেওয়া আছে, তোমরা চাইলে এই ধরনের একটা ফিগার রাখতে পারো। And how does that help us to see the thing? That is also given over here. Pulaban, all of you have the note, so pull that up and have a read through this note.
Sir.
Now,
Sir,
bolo.
can you share this again? আমার কাছে পেপার ওয়ার্কশিট ছিল, দেখে আর ডাউনলোড করি না, জানতাম না যে লাস্ট এগুলো আছে।
তোমার কাছে যে ওয়ার্কশিট আছে ওই ওয়ার্কশিটের লাস্ট পেজে এগুলো আছে, you get the physical copy, you'll find this out. This was printed with the paper to worksheet for everyone. And I really do not want to share the papers twice because of one reason. Reasonটা হচ্ছে কি রকম, আমি তোমাদের দেখাই। তোমাদের মেসেঞ্জার গ্রুপে, if you go into a messenger group, if you go into a messenger group and if you go to your message thread, I'm operating from the PC, that is, you cannot get this from your mobile এই জিনিসটা অ্যাচিভ করা কেমনে যায় আমি জানি না, আমি এখনো পর্যন্ত এটা বাই করতে পারিনি। If you use your PC from your if you browse from your PC, on the right side there are all of these tabs. Have a look. These are the five tabs or 6 tabs that you have: more actions, group actions, people, privacy, shared files, shared photos. So I have collapsed now all of them. If you just turn up this one, shared files, you'll get all the worksheets shared over here. This is very easy to access all the PDFs from here. Now, if I share it one more time, there will be 2 waves OLP2 over here, and that might be slightly confusing for everyone. That's why I prefer not to share it one more time. So get it from here. Uchi ko say?
আপনি আমার DM পাঠিয়ে দিতে পারবেন?
বুঝি না কি?
আপনি আমার প্রাইভেট চ্যাটে পাঠিয়ে দিতে পারবেন?
তুমি কই? তুমি কই?
তা আমি আব্দুল্লাহ।
এটা নাকি আব্দুল্লাহ আহন?
একটা হলে হলো, দেন এটা দিন।
না এটা না, এটা পারলে পরে আমি এটা ট্র্যাক করতে পারবো না।
স্যার
বলো।
স্যার আমাকেও পাঠাবেন?
না, আমি এখন কাউকে পাঠাবো না, এখান থেকে পড়ো এবং পরে মেসেঞ্জার থ্রেড থেকে বাই করে নিবা। লার্ন টু ইউজ ইউর রিসোর্সেস হোয়াট দে আর अवेलेबल।
স্যার আমি এটা পড়ছি স্যার, একটা অফ টপিক কোশ্চেন করে ফেলি।
না বলো, সমস্যা নাই। That's enough time to read this part. Any question about these parts? হ্যাঁ ফারদিন বলো আগে, ফারদিন বলো, তারপর আমি অন্য কোশ্চেন নিচ্ছি। গো হেড।
না স্যার, ইটস নট আ মানে কোয়েশ্চেন রিলেটেড টু ফিজিক্স। স্যার আপনাকে যদি জিজ্ঞেস করতাম যে লাইক 7:30 কে 7 to 9 করে দিতে, আপনি কি করতেন?
অন হুইচ ডে?
এভরিডে, মানে জাস্ট জিজ্ঞেস করতেছি, এখন আর লাগবে না, আপনি জাস্ট বলেন।
I could achieve this on the days that for the days that I do not have class before your class. For example, I do not have classes on the Sunday class, but before your 7:30 to 9:30 class, I have class over here, I have class over here as well. For example, this one I can do. For Sundays and the Friday class, these two classes I can make 7 to 9. I can.
আচ্ছা আচ্ছা আচ্ছা, না লাগবে না, ইটস ওকে।
এই রুটিনটা তোমাদের সবার কাছে আছে তাই না? I think so.
এক সেকেন্ড, এটা স্ক্রিনশট তুলে হ্যাঁ।
স্ক্রিনশট দেওয়া লাগবে না, আমি এই রুটিন দিয়ে দিয়েছি তোমাদের রুগিয়াতে, মেসেজে ছেড়ে দিয়ে দিয়েছি, স্ক্রিনশট নেওয়া লাগবে না বাবা।
বুঝছি স্যার।
নন কোয়ারেন্টাইন রুটিন কি আনচেঞ্জ থাকবে?
কি জিনিস বুঝি নাই?
নন কোয়ারেন্টাইন রুটিন, প্রি কোয়ারেন্টাইন রুটিন।
Yes, that will remain unchanged. All right. Anything to ask from these points, or if you have this figure over here, X-rays and UVs, read them through. If you have any question, ask me about them.
স্যার গ্যামা রে।
গামারে তো নামায় ফেললাম।
ও আমার একটু পড়তে টাইম লেগেছিল, আমি মেসেঞ্জার থেকে পড়ছিলাম।
বলো কোনটা বুঝো নাই?
স্যার ক্রিস্টাল স্পেকট্রোগ্রাফি, গ্যামা রেডিওগ্রাফি আর গজিং।
The explanations are given on the right side in square brackets.
ও স্যার গজিং এখনো প্রবলেম রয়ে গেছে।
So Gaussian mechanism বলতেছি, Gaussian mechanism simple, তোমাদের এটা বোঝানো possible, but অন্য দুইটার mechanism আমি তোমাদের বুঝাবো না, because that's very I'll have to go through a lot of stuff. Gaussian এটা হচ্ছে simple example. The idea is very simple. We want to fill up this container using coal through a conveyor belt up to a certain level. So what we're gonna do, we're gonna run this conveyor belt. When this container is empty, we're gonna run this conveyor belt at high speed, and we're gonna put all the coals and the stuffs over here pretty fast. We have set one gamma source over here, and we have a detector over here. Whenever the coals are gonna reach up to this level, because there will be additional medium other than the air that will be introduced over here, the absorption of the gamma rays would be somewhat higher compared to in the atmosphere. So the moment the level goes up this level, that this detector is gonna start receiving a smaller amount of radiation, hence giving you the information without looking inside the container. The container might as well be made from steel, so that you might not be able to look inside. So whenever this detector detects a smaller radiation than earlier, you know that this is all nearly filled up. So you then can start slowing down the conveyor belt. And when you have that lower, and then when you have the detector of this one has also lowered to a value, then you know that this container is filled up to this much. Then you can altogether stop the conveyor belt. So how much radiation are you receiving in these two detectors can tell you how fast or can you run this conveyor belt. Make sense? Hello?
No.
Okay, ask me questions.
Why is the detector connected with computer?
Because we would appreciate this process to be automated. This is a computer, but this doesn't essentially have to be a computer. It can be anything. I mean, it is a computer, but not essentially have to be a beautiful laptop like this. The idea is that whatever the the detector counts should be recorded in the computer, and depending upon how much count rate do you get over here, this would also control the motor which runs this conveyor belt, which is not shown in this figure for the sake of simplicity. So this will be an automatic system. This computer will be able to decide should we speed it up or should we slow it down, depending on how much count rate does it receive from these detectors. So this will not be manually operated. This will be an automated process. So you need more coal, so it will speed. So this computer will order the motor running this conveyor belt to speed up, and vice versa. Anything else?
No.
Acha. Anything anything from the number 2 or number 3?
Fluorescent light.
Fluorescent light. হ্যাঁ, এক্সপ্লেনেশনটা পড়ো ভেতরেরটুকু পড়ো. Try to make sense of the explanation that is already given over here, and I'll tell you about this.
স্যার এন্ডোস্কোপিটাও একটু এক্সপ্লেইন করেন এরপরে।
কোনটা?
স্যার এন্ডোস্কোপি, আই এম সরি।
আচ্ছা, sure. হ্যাঁ, I'll go for endoscopy. So this is the explanation. Here you can see a figure of it. There are two sides of the tube light. One of the coil, one of the side is made highly positive, the other side is made highly negative. And inside this tube, you have low pressure mercury vapor, not like atmospheric pressure. So there is very low pressure mercury in the atom state. So whenever we produce enough voltage across these two coil, the electrons will start leaving from the negative coil, and then they're gonna start jumping through the tube light to reach up to the positive coil. And that jumping is sort of like controlled lightning, because that's what we mean by lightning. Whenever the electrons are making their jump through empty space to reduce the voltage difference, or they're traveling from highly negative places to highly positive places, that's what we essentially call a lightning. So this is an example for a small scale lightning or controlled lightning. So in this process, the electrons are going to jump from the negative coil to the positive coil. Here they're not labeled which one is what. So from the positive coil to the negative coil, the electrons will make their jump. As they will travel through the pipe, they will collide with the mercury vapors, and that will emit the UV light. Now UV light, something is that we are not going to see, so we have introduced the fluorescent material and the inside border of the tube light. That fluorescent material will convert the UV into visible light. How does it do that conversion is not covered in our syllabus, but there's a purpose of fluorescent material to convert. They're going to absorb UV, they're going to give up visible light. If you wonder how does it happen, one of the similar example that I can tell you is that the entire idea of greenhouse effect was based upon the idea is that high temperature bodies gives up infrared waves of smaller wavelength, for example sun, which can penetrate through the greenhouse gases. But low temperature objects give out infrared radiation which have a longer wavelength, for example the earth's surface. So the sun's heat rays can easily penetrate through the greenhouse gases and get incident onto the earth's surface, get absorbed over here. But when the earth starts to radiate its own heat, those infrared waves get trapped because of the greenhouse gases. So you're having input, but you're not having output. I'm not going to say not output at all. The rate of input is more than the rate of output. So altogether, the amount of heat stored within the Earth's atmosphere, that slowly goes higher. Hence, we call it greenhouse effect.
Sir,
Yes.
sir, ক্যাথোড থেকে যে রিলিজ হয় এটাকে থার্মানিক এমিশন বলে না?
Nah, it's not going to be thermal emission because we are not using a high temperature coil. This is just a very basic regular temperature high voltage emission. You can say this is a normal. You can say this is electrostatic emission, not thermionic. Electrostatic. The only force that is causing these particles to go across is exclusively electrical energy. There is no heat energy that will introduce in the coil. The coil might get a bit heated up, but that's not so far. That's not the most important bit of the whole thing.
Sir, এখানে সেল যেটা করে, it pulls out the electrons from the anodes and puts it into the cathode, creating the voltage difference and therefore the control lightning. Right?
Yes. Okay, so that's enough. Muna, বুঝা গেছে?
জি স্যার।
Anyone else? I'm practically hearing the voice from only 3 people. Where is Yusuf? Is Yusuf not present in today's class?
ওনার ক্লাস আছে স্যার।
ইউসুফকে একটা কল দিয়ে দেখবো। ইউসুফ আমার নাম জানো কি?
মুক্তাসার।
মুক্তাসার। Have a look at my comments.
Okay. Nice.
ম্যাট্রিমোনিয়াল সাইট থেকে দিছে।
Asha, moving on. So UV has this type of things. These are the benefits, and this is the bad things. UV marks used in security. Bad things. Excessive exposure can cause skin cancer, sunburn, blistering, blindness, etc. So UV light is not that much of a good thing if you are not properly protected. That's all the reason that cricket players put those white zinc on their faces and other places so that they don't get burned by the sun over long exposure of test matches or in the sun. So that can help to get rid of that absorption of UV by the skin. Then comes the visible light. The entire point of the visible light or the endoscopy process works in a single way. First of all, what I need to understand, we are trying to see inside the body by sending a tube inside the patient's body. That tube could be sent through the oral opening or through the fecal opening or through some other opening as well. If you are having an appendicitis operation, you can essentially have a cut in your belly in the appropriate location, and they can send this tube, and the doctor should be able to see what's over there. Benefit ta hocche, you don't have to cut open a large amount of space on your skin, so you'll have a very small incision mark, and also it's good for observation. But one of the key part that I really need to understand, inside the body there is no light source. The way we can essentially see anything is that light from an external source should fall onto an object, get reflected off that object, and that reflection is what will be seen as that object. So you need to have light falling onto the object. So primarily you have to illuminate that object that you want to see, and then that illumination will give you the reflection of the object surface, and then we'll be able to see this thing. This is why for the endoscopy tube, this is the long endoscopy tube which will be put inside the patient, but it essentially is made up from 2 optical fibers. Through 1 optical fiber we send the light. This optical fiber goes to here, comes out of this objective lens and illuminates the body parts over here. Then that light gets reflected off, and then it enters through this pipe and comes to the eye of the doctor. The doctor can see this. So you need to have 2 channels of light over here. One to illuminate the inside the patient's body, whatever that organ that you're trying to see inside the patient's body, and the other one to convey that reflected light back to the doctor's eye so that they can see this thing.
Sir,
Yes.
So optical fibers advertise গুলো বলতে পারবেন?
Optical fiber is practically a device that can make optical fiber concept আমি একটু পরে আবার ডিটেইলস আলাপ করব, লাইক চ্যাপ্টার যখন করব তখন optical fiber পুরো কনসেপ্ট আরো ডিটেইলসে আসবে. I will cover this, not for the time being. I'll cover this. It will be covered in our set of discussion, no big deal. Infrared এর সবচেয়ে কমন ইউজ হচ্ছে এটা, remote controls. Then we have night vision, then we can do cooking, then this. Sorry,
Night vision take to explain Corbin, please.
Night vision basic idea is very much like UV light. I mean, the material which is called a fluorescent material can convert the UV into visible light. Similarly, there are some certain other materials which can convert the infrared light into visible light. If you make some goggles or make some camera lenses using that material, which can convert infrared into visible light, you get night vision. So now you're seeing, now you're trying to detect the location of an object by the amount of heat they are radiating, not essentially by visible light, because our eyes are sensitive to the visible light spectrum, so we cannot see any of the other spectrum. So if we have to see the other spectrum, we need to have some sort of converter. So for UV light, that converter is what we call the fluorescent material. For infrared wave, there is another type of converter which is not given a name over here, but that also converts the infrared light into our eye detectable visible light. That's what night vision is all about.
Sir, why is the night vision like that?
The night vision is like that because we cannot make sense of the color of the object for the case of a night vision, but what we can differentiate is that amount of radiation that is given up. For example, the car is a hot object, the persons are hot object, everything else is not hot. So these things are giving out here. For example, the top of the front of the car where the engine is located is warmer compared to the rest of the car. So you have this part more brighter compared to the rest of the car, and the persons are also very much like that.
Sir, why don't we understand the color? It is the visible light that rays are being converted into.
No, it is the infrared rays which has been converted into visible light for our convenience. It's not the exact visible light directly taken off from the person. This location that we are trying to see using the infrared camera is absolutely dark. So there is no visible light falling onto them, and they are not being visible. They are not being seen by the exact visible light. They are emitting infrared lights which are converted into visible light for our convenience.
And it has its limitations, right?
It has its limitation. It can work with the intensity or the amount of infrared light that is, but it cannot work with the color.
Yes, sir, understood. Thanks.
Beautiful. Tarpor, microwave.
Microwave concept একটু বুঝাবেন?
Poro. Help yourself first.
স্যার এটা কি ভাই? স্যার এটা কি?
কি লিখে আছে? হেডিং গুলা বড়, ফিগারের একটা নাম আছে নিচে, ফিগারের নিচে সেগুলো পড়ো।
যে জিনিসটা আমি বুঝিনি সেটা হচ্ছে the infrared rays are the electromagnetic expressions of heat. তো মাইক্রোওয়েভ আবার কিভাবে হিট করলো?
Microwave exclusively get absorbed in the water molecules because of a specific matchup between the wavelength of the microwave and the water molecules constituent particle, hydrogen and oxygen's atomic level energy distribution. Now this sentence that I'm just told you is not a part of a syllabus. You don't have to remember that. Simply put, water molecules can absorb microwave efficiently. So if you send microwaves into a thing that has water molecules in it, that object, I mean, it's possible that the other substance molecules might as well not absorb microwave radiation, but the water molecules will very eagerly start absorbing microwave waves. And whenever they will absorb those microwaves, their energy amount is going to go higher, which would be immediately expressed as heat.
And that is radiated by the water molecules to the other food molecules, which then absorb the heat molecules and become hot.
Yes.
And since sir, if the food is completely dry, then would the process work?
No matter whatever, if you want to define this as a food, the food might be dry, but the water content would not be 0%. You cannot make food without water.
As it is a part of the organic things, right?
Exactly.
Carbon, hydrogen, oxygen.
So, exactly. It might appear to be dry. For example, let's say a very dry cookie, but that dry cookie might have a very small water concentration, but that amount is not essentially zero. So microwave heating works pretty much on all sorts of stuffs which has water in it.
So can we somehow take all the water out?
To achieve the content.
You actually can take all the water out of an object, but once you take all the water out of an object, first of all, this is not going to be a very edible food. One of the ways we can actually dehydrate an object completely is by having it submerged in a very concentrated acid solution. If you have, let's say, really concentrated acid and you put some object from which you would like to extract out the water, acid molecules are going to pull out all the water out of that object, because water is slightly positive negative, and acid molecules easily decompose. Acid molecules easily break down into positive and negative parts. So they are going to do attraction and pull out, if they can effectively pull out all the water. So that can happen. So if you can 100% dehydrate an object, logically microwave would not work on them.
Oh wow.
We would never try because we would not eat them.
What's the practical use of it? I mean, why should we? You can do this if you want, but is it useful? In most cases, no. One of the other things that I would like to discuss, that you can see that on the upper right corner there is two rectangular things are located which read special electric circuits produce microwaves. So we have the it is the fan. So the microwaves are produced, and then there is a fan-like thing on the top that is labeled as reflectors and microwave in all directions. So we usually have moving reflector, so that the reflector. So we usually have a reflector, moving or not, that will be sending those microwaves spreading out in all directions. But those microwaves might not as well reach for every part of the food evenly, no matter how good of a reflector you design. To achieve even heating of the food, that's why we have a rotating plate in all the microwaves. So that using a rotating plate, you can pretty much uniformly heat up your food in all places. If you don't have the rotating plate, then once you heat up, it is very much possible that part of the food, certain locations of the food might be very hot, certain locations of the food might not be as much hot, because it's all depends on where your microwaves are getting absorbed. To have an uniform heating, we need to have that rotation.
The rotation, the fan rotation.
The food bowl rotation by a rotating disc at the bottom of the food bowl.
Understand its purpose now. Thanks.
Sure. Moving on, radio waves, simple thing. There's nothing very complicated for this. আচ্ছা, I just remember তোমাদেরকে আজকে সাউন্ড ওয়েভে দুটো এক্সপেরিমেন্ট পড়ানোর কথা ছিল, তারপর আমার ওয়ার্কশপ সলভ করার কথা ছিল, রাইট? ওয়ার্কশপ সলভ করার প্ল্যান ছিল, বাট देयर were two experiments which was left in the sound chapter. হ্যাঁ, ইকোর উপর বেস করে দুইটা এক্সপেরিমেন্ট আছে, ওটা তোমাদেরকে লাস্ট ক্লাসে আমি বলছিলাম যে আজকে ফার্স্টে ওটা পড়াবো। আচ্ছা, this is since I remember this one, I'll definitely do this, but let's go ahead with the task at hand. Any question about the radio wave? You should say no. রিপল ট্যাগের এখানে একটা ফিগার আছে, ফিগারটা তোমরা অলরেডি জানো। There is a small bit of description over here. I need all of you to read the description and ask me questions if you have any about the description part, from the description part. If you have any
question that জিজ্ঞেস করতে ভুলে গেছিলাম, what is the difference between telecommunication and radio communication?
It's about the choice of the electromagnetic spectrum that you will use to do the communication. There is practically there is almost no difference in the structure or the complicacy level of the devices, but it's about what range or what specific part of the electromagnetic spectrum do you want to use for your equipments. If you use microwave, it's microwave communication. If you use radio waves, it's radio wave communication.
Sir, is it right if I say that the radio waves do not have enough small wavelength to penetrate the atmosphere and therefore stays within Earth, therefore used for communication within Earth, but microwaves have that ability?
I did not get your point right. Radio waves do not have enough what?
Sir, let me rephrase that. Radio waves have a large wavelength, so they cannot penetrate the atmosphere. And for microwaves, they have a smaller wavelength, and therefore they can penetrate the atmosphere. Telecommunication is but not radio waves, which are used for Earth's communication.
No, that's not a valid reason, as far as I know. There are other reasons, but whatever you said is not a valid reason for what you are trying to put it for.
Then what is, sir, this?
Class শেষ করে পরে বলিও।
Okay.
আচ্ছা, জিজ্ঞেস করে আমাকে, I'll help. No video. For the time being, go through the description. Anyone, any question about this description? I'll move to other parts.
No, sir.
রিপেল ট্যাঙ্ক ইউজ করে শুধু রিফ্লেকশন দেখানোর জন্য না?
আবার বলো, বুঝি নাই, একটু জোরে বলো।
রিপেল ট্যাঙ্ক ইউজ করে শুধু রিফ্লেকশন আর রিফ্রাকশন দেখানোর জন্য।
We are not having reflection in a repel tank per se. I mean, which waves reflection are we talking about, or are you talking about?
Whatever.
Yes, we can. Yes, we actually use repel tank to have a visualized experience for how the waves work out. Because I mean, you can have reflection of sound wave or light wave, which is the most two usually common waves that we are surrounded by. But none of those waves are visible by their own virtue. So you need to have some sort of a conversion mechanism or some sort of similar mechanism so that we can actually see those waves. Ripple tank basically does that. We make the water waves to get an idea for how the other waves also behave.
আমরা কি ডিফ্রাকশনও দেখাতে পারবো?
হ্যাঁ, ডিফ্রেকশন দেখাতে পারবো। ডিফ্রেকশন আমাদের পড়া নেই, ডিফ্রেকশন পড়াবো একটু পর।
স্যার ট্রাফ হলে যে ব্রাইট হয় আর ক্রেস্ট হলে যে ডাল হয়, why is it like that? Reflection?
No, this is because of the depth of the medium or the curvature of the medium, which causes certain parts of the water medium to work as a convex lens, alternate parts work as concave lens.
Oh, this is why the troughs are brighter, the crests are duller.
Ulta also. Ulta also.
Concave হলে diverging আর convex হলে converging, তাহলে ক্রেস্টে হবে ব্রাইট আর ট্রাফে হবে ডাল, right sir?
Yes.
Thanks sir.
No problem. So moving on from this part, this was the part that I wanted to discuss because this was required for our MCQ discussion. So I'll be getting back to the place where I came from, illuminated spectrums and use. So you tell me about the problems from 9.4. Anything from page number 1? If you have already have some problems, you now have gone through the literature that you needed to help with. So you read it again. If you have any question, you ask me about it. Anything from page number 7 or 8?
Sir, 9.5 এর প্রবলেম আছে।
হ্যাঁ, 9.4 যাচ্ছি। 9.4 এর কোনো প্রবলেম আছে কিনা দেখো।
No, sir.
Anyone else? Zola. 9.5 দেখো, moving on. 9.5. These are good questions, so I'll take my time in detailing these questions. So you go one by one. Page number 9.
Sir, number 8 এর প্রবলেম is correct.
আচ্ছা, নাম্বার 8 এ যাবো, সমস্যা নাই। পেজ নাম্বার 9 এর কোন প্রবলেম আছে কিনা দেখো। কোশ্চেন নাম্বার 1 through 7.
Sir, 7.
আচ্ছা, 7 এর বেসিক আইডিয়া যেটা খেয়াল করতে হবে, y axis এর নাম হচ্ছে ডিসপ্লেসমেন্ট, x axis এর নাম হচ্ছে টাইম। If your x axis is time, then one full cycle represents time period, not wavelength. If your x axis name is distance, then one full wavelength represents wavelength. So you have to be careful to observe what is the name of your horizontal axis. If the horizontal axis is time, it means this graph is a displacement versus time graph for one particle of that medium, of that wave. How is it moving up and down with respect to time? That's what is shown on this figure. This is not the actual shape of the wave. This is a time-based plotted graph, or this is a made graph. This is one scenario. So if you have time on the x-axis, then one cycle length represent time period.
Got it, sir.
আচ্ছা, alternately যেটা বলতেছিলাম সেটা হচ্ছে if you have a graph like this, distance versus distance, this is the actual shape of the wave looked from the side. In this case, one full cycle represents wavelength. Make sense?
Yes sir, thanks.
Sure. Next thing হচ্ছে নাম্বার 9 বলছিলা কেউ জন?
Sir, 8.
8টা পড়ে দেখো, এখানে ওয়েভ ডিউরেশন দেওয়া আছে। The wave duration is labeled over here. So all that you need to distinguish that how would you describe P and how would you describe Q? Is P a particle in front of a crest or in front of a trough?
In front of a trough, particle P.
It's supposed to be in front of a trough, although there is no trough plotted over here, but you can see that it is behind the
Yes,
crest.
sir.
So it's in front of a trough, which means this is going downwards.
To the right.
Right?
Yes, sir.
Yes.
And this one is going upwards. So in the very next incident, P will move down and Q will move up. So have a look which one makes your does your job. Q will move up. C is the correct response. No, sorry, D is the correct response.
Hi, sir. Good.
Acha. Before I get into the sound MCQ, I would like to discuss those experiments that we have had. Sorry, that was autonomous.
স্যার কিউ না ইকুইলিব্রিয়ামে আছে?
স্যার আপনার বিড়ালদের প্রতি এত ভালোবাসা কবে থেকে জন্মাইছে?
It just happened randomly.
ওকে, বাট when?
তুমি জবে থেকে জন্মাইছো।
No.
তখন থেকে মানুষের ভালোবাসা উঠে গেছে।
I don't recall the exact date, but my first cat was Juglu Potash. I think it was I think 4 years back. I had my first cat, and I was already in this building. I walked out of my building after a class, and I was having a chat with 2 of my colleagues, and then I found this one cat which came close to me and was mewing. I called it in, and it did come with me, but he didn't believe me first. So I gave him some food. He ate it, and after he ate the food, he got stuck with me, like literally. I mean, and since then it started. It was not planned at all. Yes.
It was an accident, just like Fardin.
স্যার কিউ না ইকুইলিব্রিয়ামে, তাহলে এটা মুভ করবে কেন?
I'll highly recommend that you go through the discussion of the part of the video that we did discuss over here about this part. And if you have any further question, ask me in person. No big deal. আমি এখানে কেন ঢুকছি? আচ্ছা, I wanted to find this way now. Yep. So we have over here Zubair's class notes, which are.
স্যার আপনি ওয়ারজোন খেলেন?
না, আমি এগুলো পাই না। অপ্রয়োজনীয় জিনিস চ্যাট মেনুতে লিখো না। If you have something important to write, please do so, but don't write weird stuffs or unnecessary stuffs.
স্যার আপনার অনলাইন ক্লাস ভালো লাগে?
Online classes?
জি, ভালো লাগে নিতে নাকি ফিজিক্যাল ক্লাস ফেস টু ফেস?
I'm okay, but I'm not comfortable.
স্যার আপনি বলতেন you like it a lot online classes.
I like it a lot for the comfort that I am. The aspect that I don't like is that I cannot see the face of the students, so that I don't know how much they are understanding. That from that part, I'm entirely blind. I cannot actually find the exact experience that I'm looking for over here, which I might look for some other kid. আরেকটা জন কে পড়াইছিল আমাকে ক্লাস নোটস? অদম্য না অপ্রতিম মনে হয়। Yes, I think. No, not অপ্রতিম। আরেকটা জন কে নোট পাঠাইছিল আমাকে?
আমি পাঠাইছিলাম স্যার।
বিপ্রো তুমি পাঠাইছিলে নাজিফের নোটস, রাইট?
হ্যাঁ।
রাইট।
না স্যার আমার আম্মুর নামে।
আম্মুর নাম হচ্ছে
মিতা সরকার।
রাইট। Got it. Acha, I might as well be able to find this. So I'll go shared photos. And wow, this is so good. So good. So good. একলা পরে বান্ধে বহুত কিছু লিখাইতাম।
এখন কি হইছে?
এখন এখন পর্যন্ত কিছু হয় নাই। আচ্ছা, yes, I might as well start from here. So first of all, I would like to talk about, can you please read this thing? Acha, it's not essential that you should be able to read this thing. I'm portion আছে. Audible range is the effective range or the practical range of sound frequency that we human beings are engineerily capable to hear. I'm using the word engineerily because that is the range that humans can hear as a species, but every single human being might not be able to be sensitive, might not be sensitive to this whole range. The audible range of human beings is measured from about 20 hertz to 20,000 hertz, which means that sound waves as with frequency as low as 20 hertz can still be heard. Sound waves as high as 20,000 hertz can still be heard. So that's a pretty large range that we are sensitive to. But as people get older, it's possible that their range might become smaller on both sides. Smaller on both sides, their lowest frequency heard might become bigger. Maybe they will be able to hear from 100 hertz and on upwards. Maybe frequencies lower than 100 hertz might not be audible, and it will become smaller on the top side as well. So they might be able to hear up to 15,000 hertz, but they might not be able to hear above 15,000 hertz. So it's possible that though that range can be different for different people, but on a standard case, we say the audible range for human beings is 20 hertz to 20,000 hertz. Any sound that has a lower frequency than the lowest audible frequency, able to see any sound that has a lower frequency than the lowest audible frequency, that is sound frequencies with less than 20 hertz vibration, they are called infrasound. Infra generally means small and ultra usually means large. One of the key parts where you have come across this idea is that if you think about the EM spectrum, electromagnetic spectrum, and going down with frequency, the highest frequency electromagnetic spectrum, it has which name? What is the name of the highest frequency electromagnetic spectrum? Anyone?
Yes, sir.
Which electromagnetic spectrum has the highest frequency?
Gamma
Gamma rays. So on the very top we have gamma rays, then we have X-ray, then we have UV, then we have visible light. Now, what I need you to understand that visible, the 7 different colors that we define that exist within the visible light, as per Isaac Newton, is Viv gear. So violet, indigo, blue, yellow. Violet, Viv gear. Violet, indigo, blue, green, yellow, orange, red. So the highest frequency in the visible spectrum is violet. The frequency that is above that range is named ultraviolet. Ultra in this case means higher. And in the same way, the lowest frequency in the visible spectrum is red. The the electromagnetic spectrum that is below that red range is what we are calling infrared. Infra means smaller. So ultra means larger typically, and not typically. Ultra means higher and infra means smaller. So ultraviolet means a frequency higher than the violet color. Infrared means a frequency lower than the red color. Similarly, for the case of sound, infrasounds mean sound waves with less than 20 hertz vibration, and ultrasounds means sound waves with more than 20 kilohertz or 20,000 hertz vibration. So vibration, now I should use the term frequency. So sound waves less than 20 hertz frequency are infrasounds. Sound waves with more than 20,000 hertz frequency are ultrasounds. So that's the idea of audible range. Beyond this point, we have some actual usage of the of the sound. One of the key part that is shown over here is that we can use hold up. It's amazing how effectively messenger messes up these stuffs. বলতেছি এই যে পাইছি uses of ultrasound. So আমাদের সাউন্ডের ইউজেসের মধ্যে অনেকগুলো জিনিসপত্র আছে. I'm going to be covering pretty much all of it so that it's understandable for you. The first one is that it's called sonar. Can you আচ্ছা আমি এটা কপি করে আমি এটা আমার ইয়াতে নিয়ে যাই যাতে করে আমি এটা দেখাইতে পারি তোমাদেরকে আমি এটা তোমাদেরকে আজকে রাতে সব গুছায় প্রিন্ট করে পিডিএফ বানাই দিব. So don't worry about this. Can you please read it, everyone?
Yes.
Uses of ultrasound. Sonar. Sonar stands for sound and navigation and ranging. So what kind of people made this kind of short form? I don't know. They took S and O out of sound, and they didn't take this end, but they did take this end. So they made it sonar. Anyway, weird, but that works. Sonar stands for ultrasound waves are used to measure depth of seas / find large group of fishes for easier fishing or detect maneuver through unclear water or / detect and destroy enemy water vessels, etc. So basic idea, you cannot see through the water, but you want to see what's beneath that water, what's in front of that water. You can use high frequency sound. How does that work? Have a look. The key to this use includes sending different frequency ultrasound pulses in all directions. Slightly different frequency sounds are sent in all directions. If sound waves are reflected off an obstacle, a very small portion comes back to the source. This is basically how we talk. So what we're going to do is that the device, that vessel is going to produce a small pulse of a certain ultrasound frequency, and it will be reflected off something that is away. We are seeing a small portion because you have to understand that whenever you start making energy or wave energy from a source, that wave energy spreads out as it goes farther away, right? Think about this. If you think the wave energy gets spreads out. So we talked about this in detail in an earlier class. So because the wave energy gets spread out, whenever it will hit an obstacle, not all of your energy will hit that obstacle. A small portion of your send energy is going to hit that obstacle. Then that obstacle is going to reflect that amount of energy that it was that fell onto it. So a small portion of energy is falling onto the obstacle in the first place, and when that obstacle will start to vibrate, not essential that this obstacle is a flat surface. It could be a curved surface. It could be the geographic, I mean the ocean surface or on the other vessel surfaces over there. So they could have curves over here. It's not essential that those reflection surfaces are perfectly flat. So whenever those surfaces would do that reflection, they're also going to disperse out that vibration. So a small portion is received, and when that reflection is made of that obstacle, that is also going out in all directions. But it is possible even a very small portion of that energy might actually end up reaching that source. And that's exactly what we are willing to find out. We use very sensitive detection mechanism. So we make a sound, and then we receive the reflection. And then as it reaches over here, have a look. The key to this use includes sending different frequency ultrasound pulses in all directions. If sound waves reflected off an obstacle, a very small portion comes back to the source. The transceiver is a common word which is made from transmitter and receiver. Together we call it a transceiver. The transceiver device detects this reflection, which is actually an echo. The reflection of sound is called echo, which is a good name that we have given it, and can pinpoint the location of the obstacle by doing calculations by v equals to 2d by t. আচ্ছা এই জিনিসটা কি সেটা আমি একটু পরে বলতেছি. আচ্ছা এখনই বলি, সমস্যা নাই, আমি এখানে এঁকে দেখাই. মনে করো এটা হচ্ছে তোমার সাবমেরিন কেমন আঁকে, মনে করো এটা হচ্ছে তোমার সাবমেরিন. This is the head, this is the tail, and here is the propeller. Okay, so and in front of your submarine, let's say some part over here we have megalodon. What is megalodon?
The largest shark species ever to exist.
So you cannot even see the whole body of the megalodon. You can only see its smiley face and teeth and that thing. Okay, so let's say we have megalodon over here. We don't want to get inside, so we do not want to get inside. So what we are doing, we're going to send our pulses over here. It is going to get reflected off the megalodon's body and come back. So let's say I mean, you have to understand one thing: the movement of this vessel is a limited value. So they might as well move at. I mean, under the water, the speed of the vessels are not as fast as land vehicles or in air vehicles. So they have a speed of their own, but the sound will travel through the water at a much higher speed, because water is a liquid medium. The particles are pretty close. So compared to air, the sound wave in water travels faster. So it's going to travel from the source to the megalodon, and eventually a portion of it is going to come back. So if we assume that the distance between the megalodon teeth, let's say this is the part where you have the reflex. So I'm drawing this line over here. So if you assume that this much distance is d, what I need you to understand very clearly, that this sound wave has to go forward and fall backward. So how much was the distance covered in this traveling?
2D.
2D, right?
Yes, sir.
So what this device does, it sends out a pulse and waits for to hear that reflection. Whenever it detects the reflection, the amount of time it takes for the reflection to reach to the source is twice the distance between the source and the object. So we can essentially get v equals to 2d by d. We can write this equation, and from this equation we can subject that d. D will be given by vt by 2. So we can very easily, very precisely measure that what is the exact distance from here to that here, from here to that megalodon. So only knowing the distance is not good enough. What this thing does, it keeps on repeating this process. This sending mechanism keeps on repeating this process. So you can measure, you can get that distance information at, let's say, 0.00 second. Then you can get that information at 0.01 second. You can get the distance in 0.02 second. So for every 0.1 second variation, you are measuring the distance every once in a while. So from here, you can very well get an idea that are we getting closer to this, or are we getting farther away from this, or even what is our acceleration towards the object, because you have distance versus time data from the use of the sonar mechanism. Do I make sense?
This sonar mechanism sends out the ultrasounds in every direction.
Yes, the ultrasound is sent out in every direction. A small portion is reflected off over here. Let's say the reflection is shown by this one. That reflection is also small. So the part that eventually comes back is extremely small compared to what was sent outwards. But the receiving mechanism is sensitive enough to be able to pick that up as well. That's how it's designed.
Yes, sir.
Bolo, Argentina boltesila. Hey, Tashfia, you can.
So did you watch the movie The Core?
Acha, sorry. Rahmalik হচ্ছে sonar sound navigation and ranging. আচ্ছা এখানে মাঝখানে end হবে না. আচ্ছা, my bad. I think my student actually wrote the und as a second end. So yeah, thanks for the correction. So okay.
Sir,
বলো।
ওই যে The Core মুভিটা দেখছেন?
না, ওখানে কি হয়?
স্যার ওখানে লাইক আচ্ছা দেখার পর আই থিংক বুঝবেন। ওখানে লাস্টের দিকে লাইক মানে দ্য সাবমারিন লাইক ওটা হচ্ছে জাস্ট নিচে পড়েছিল অন দ্য সিবেড। সো টু গেট দ্য মানে টু ডিটেক্ট দ্যাট ডিড দে ইউজ সোনার অর নট, আই ওয়ান্ট টু নো দ্যাট।
Achha, yes, I might have a look at it. The most recent water-based movie that I saw, and I pretty much felt pretty good at this, was that movie that there came an alien spaceship in the water who made an electrostatic wall around a globe, and instead there were 5 ships that got trapped.
Battleship.
Yeah, I really like that movie. Not because of the idea
that movie is really good.
But the actions are good. I mean, it gives you good feeling that yeah, we human beings are artificially, we feel like that we are good because we can kill all the alien species who could travel billions of miles of distance but cannot work with human brain. I mean, that's just crap. But we like it. I like it because the action looks good.
Yes, sir. It did look good.
স্যার মুভিটা দেখে একটু বলেন তো was that sonar or not?
আচ্ছা ঠিক আছে, I'll have a look into it. রাখো।
স্যার যদি ডিসটেন্স হয় যে ওয়েভটা চতুর্দিকে ছড়া দেয়, দেন দ্য ডিসটেন্স দিস ডি এটা দিয়ে তো একটা it could be anywhere from D. It could be downward.
No, not essentially. I'll tell you why not essential. Because we are assuming that this water wave has pretty much uniform density over this area. We are assuming it. So so if the sound wave has to reach to you, the sending out and the reflection back, that has to happen in a straight line. I mean,
is it a law?
বুঝি নাই। Now you might wonder what if this reflection happens from a secondary source. Secondary source থেকে হলে কি হবে সেটা আমি তোমাদের একটু পরে দেখাচ্ছি, but I'll cover that part in a bit, but I need you to I need everyone to comply that. Did you understand the idea of this equation and ultimately this calculation and this idea of obtaining all the distance data after for every time instances? Did you get this part? মানে possible এটা বুঝা যাচ্ছে কিনা?
Yes, sir.
Yes, sir. It's clear.
That's beautiful. That's how basically any echolocation or sonar device work. This is also the exact mechanism by which bats move around at the night. Through their vocal cords, they make really high pitch ultrasound, ultra frequency sound, which spreads out in all direction, and then they reflect those reflections. And from those reflections, they can understand exactly what is located where, what kind of an obstacle is there, and in which direction they're gonna be able to they're gonna move. This is why they prefer to can move without any trouble at nights, because they do not essentially use light for their viewing. They use echolocation. Echolocation means the location mechanism of an object by echo. That's a word, actual English word, echolocation. So they use that. In the Batman movie, I think in the Dark Knight movie, there was a centralized observation chamber that Morgan Freeman built. Do you remember that they used every mobile device into echolocation device?
Yes.
That was that
জোকার ছিল যে মুভিটাতে জোকার অনেক জ্বালাইতেছিল।
Exactly. So to find out where Joker is or what he is doing, by some mechanism, by planting a virus into all of the cell phones, they converted every cell phone in Gotham City echolocation device, and they could capture their data, and they could know what people or what things are around that thing, so that they could surveil everyone instantaneously. Remember that shot? Anyone?
Yes.
Yes, sir.
Let me just help. I just told you the reference. You can look it up on your own time. I am not going to get into this deeper than I have already. But I'm trying to give you a good idea for what we are discussing, because it's important that you understand the concepts in the first place. Otherwise, it's all futile. It's not very useful. Notes ta gelo koi? Left e chilo. Sorry. So this is the part of the echolocation. So এখানে যদি দেখো, because 2D by T, multiple scans can give information about the obstacle, if it is a whale or another submarine or a torpedo, for its velocity and acceleration. So multiple distance information can give us every other information that we need. That what is this velocity, in which direction it is going by, what is its trajectory, is it accelerating or is it decelerating, is it stationary, what kind of reflection are we having. If we have a reflection that is pretty smooth or pretty orderly, you can pretty much think that this is coming from a man-made surface. For example, if you get the reflection out of an enemy submarine, then you will have a pretty smooth curved surface, which will give you the vibration. So you will be able to detect a pretty uniform vibration. So those informations are also analyzed through the sonar technology, and that can give you a lot of information about what is around. So in that, and the further it says that in the equation v equals to speed of the sound in the seawater depends on salt concentration and temperature of the seawater, and is known by the sonar device. So it is a pre-entered data into the sonar device. So sonar device is fed the information v. এই যে ডি ক্যালকুলেট করার জন্য যে ভি লাগবে, এই ভিটা অলরেডি সোনার মেশিনকে খাওয়াই দেওয়া হয়, যে আমি বলে দিতেছি স্পিড অফ দ্য ওয়াটার, স্পিড অফ দ্য সাউন্ড ইন ওয়াটার, সি ওয়াটার ইজ দিস মাচ, and then t equals to time for sound to go to obstacle and reflect back, comma d equals to in between distance. Since the distance is covered twice, there is a 2 in the equation. এখানে just 2d by t equation expression বলে দিয়েছে. This is one of the, so this is a simple example that I made to make it interesting, but this is also another experiment that we can show you. We'll say that the typical fishing boats that do fishing in the seas, they don't randomly put their nets in places of the ocean and capture and expect to get a lot of fishes out. So what they do, they from the bottom of their ships, they send out ultrasound pulses. Now, if there is no ship, no fishes in that water, they're gonna receive the reflection directly of the seabed or the bottom part of the sea. So using that part, they can essentially detect how deep is the water. That's a measurement they can make. That's one thing. But if there are some group of fishes or shoal of fish in this part, then they would also get some random reflections from the sorry, they would also get some random reflections from the fish bodies as well. So they are gonna get a pretty strong reflection of the seabed because this is a solid surface, but the reflections of the fishes are not gonna be that much strong. So it is possible that they might come up with a diagram which might as well look like this. Which might as well look like this. So let's say আচ্ছা এটা হচ্ছে একটা সার্টেন জিনিস। এই জিনিসটা এই ফিগারটা কি মিন করতেছে সেটা আমি বলতেছি। This is I mean the source which sends out the sound and the receiver or the transceiver is connected with the cathode oscilloscope as well. The cathode oscilloscope is the detection mechanism, that's not the driving mechanism. So whenever the send pulse মানে হচ্ছে it's a small high energetic sound, not a continuous sound. For example, a clap is a pulse kind of sound. A sharp scream like ah, that's a pulse kind of sound. It's and a continuous sound would be like that's a continuous sound. Sonar always works with pulse kind of sounds. We send pulses of sounds because we have to give the device enough time to detect the reflection as well. So this is a figure. This one is a figure that is seen on the cathode oscilloscope screen. I did not show you all the parts just to make it simpler. So whenever the sound is sent sound is made, that's a really high energetic sound that gives us a huge amount of vibration. So you get a pretty large amplitude over here, and you get the energy is very high. Now that sound is traveling forward, and it is reflected off the seabed. So you get a pretty solid reflection over here. That's a pretty solid line, and that represents the seabed. If fishes are in between, you're gonna get some disturbances of reflections over here. So these things are going to be present if there is something discontinuous medium, for example fish bodies, which is a discontinuous medium, not like a hull. Discontinuous means that there are multiple fishes which are giving you multiple reflections, so you're going to get some random reflections over in between. Expert fishermen will see this and they will know that there is a fish, a group of fish over here, and then they can cast their net. So this is one way by which fishing can be made easier. Does it make sense?
Yes, sir.
That number 2 that we have is that ultrasound cleaning. This is pretty simple. This is the key process for any clean this is the key process for any cleaning hobe na, eta hobe dry cleaning. I think my handwriting was very bad, so this kid made a mistake. This is not the key for any cleaning. This is the key process for dry cleaning. For here, the object is placed in a container which where it is vibrated using ultrasound waves pass through the atmosphere. The air molecules, by their vibrations, shakes the dust and dirt of the object.
The vibration is that powerful to do that?
Yes, it's an ultrasound vibration, so the frequency is very high. I mean, there is a logical limit for how much of a powerful vibration that you can provide to that cloth. I mean, too much high powerful vibration might as well tear off the fibers of the cloth. So we are not going to reach to that level, but we're going to reach to the level so that the darts and the dust, they can be shaken off. Get the idea?
Yes, sir. Understood.
So there is a very sensitive value or range or magnitude of how much you can go. Going all the way might as well make your entire cloth into dust. That's something that we do not want to have. It's possible. And then so to clean precious watches, it is used often. Acha, eta hocche je mechanical watches can be really costly. Mechanical watches are those which do not run on battery or not digital. They have a spring-loaded mechanism which can run for a year. You have to wind it every once in a while. Mechanical watches are sort of like a novelty or a really high-end product currently. So mechanical watches, if they get old and if they get dusty, small dust particles can cause you to lose, let's say, minutes over a day. So if you lose 1 minute every day, then every 5 day or after every 7 day, after 1 week, your watch is gonna be, clock is gonna be, let's say 7 minutes late compared to that. So you have to continuously readjust your time. So one of the ways we can get rid of this kind of troubles which can happen over a long period of usage is that you can put those things, we can open this up and put all of those stuffs inside this kind of a dry cleaning device, ultrasound dry cleaning device, and all the darts and those things, they can be shaken off from the parts of the clock and they're gonna fall down on the chamber and you are good with it. So that's possible to achieve. And then the third use that we have is called prenatal scanning. Channel mute karo. The idea of prenatal scanning looks like this. So let's say this is a cross section of a pregnant woman. So have a look. This is a cross section, that is, you're looking from on the top. So this is the belly part, and this is the backbone. So this figure is not drawn to scale. Neither this figure is absolutely accurate. So, but try to make sense out of it. Let's say this is the backbone. So these are the extensions of the backbone, which essentially make the rib cages or other parts. This thing is the vertebral column, which is the centrums of the vertebra stacked one upon another, and makes the entire vertebral column. So this is the part that we have. In front of this thing, let's say this is the whole body, and there can be a lot of other stuffs. Let's say this outer covering is the womb. It is the bag in which the baby exists, and there's amniotic fluid over here, and this is this hash thing. Let's say this is the baby. Do you understand the meaning of this picture, everyone?
Yes, sir.
Okay, so we want to find out the location of this baby and how this baby is oriented, or is it healthy or not, by doing echolocation. If you wonder why do you want to do this, first of all, we shouldn't use X-rays over onto an unborn baby, because X-ray waves have good enough capability to mutate the cells of human body. Now, if I, an adult person, go into an X-ray machine and have my X-ray done, my immune system is strong enough, or my immune system is good enough to deal with the mutated cells that I might have. But for a baby, that's not the case. If a baby is primarily small, if you scan a baby using X-rays, it might actually damage a significant number of cells in their body. And because a baby is a very fast-growing organism, so its immune system might not be able to capture and remove all those mutated cells, so which might get built into a tumor or cancer growth within that baby. So it is never recommended to use X-rays on pregnant women. That's why we are taking refuge to echolocation to go work with the baby, because echolocation is not electromagnetic waves; it's just a sound wave of physical vibration. So that's better compared to X-ray. Does this aspect make sense?
The same job as the X-ray, but does that in a form of vibrations instead of electromagnetic spectrum, which works, right? So it does the same work of the electromagnetic rays in the sounds form, which is vibration of the air molecules or vibration of the medium.
Yeah, it does pretty much the same job of analysis, but it doesn't work with high energetic photon particles or high energetic electromagnetic waves. It does it by vibration, yes.
Yes, this vibration is not detrimental to either the woman or the baby, right?
Yes. But then again, this data is not as accurate as X-ray. But then again, we would appreciate safety over data accuracy for an unborn baby, that is. I mean, if you compare the accuracy of data or information between an X-ray image and between an ultrasound image, an X-ray image is far too detailed and far too accurate and good, vivid, and can give you even very precise information. But your echolocation or ultrasound scanning cannot give you that much information. But it serves a function that we want to deal with the baby with. So moving on, so the way it works is that, let's say this is the transceiver mechanism, which should be placed onto the patient's or on the mother's womb, and this will be moved around. The way we work is that we send a small pulse, small ultrasound frequency pulse. If you wonder what do you mean by small in this case means a pulse that is short-lived, like tick, not tick. By mentioning the word small, I do not mean its volume. By mentioning small, I mean its duration. So we send a small ultrasound pulse from here, and it is aimed towards the backbone, because backbone is the strongest of all the stuff that exists over here. So this gives you the strongest of the reflections. What happens, this wave travels through all of this in different mediums. So first it penetrates to the skin, then it penetrates to the fat layer. If you think of the human body, for those who have biology, you should know this. So I haven't drawn all of these layers that I'm talking right now, but I need you to try to understand. It enters into the skin, then it goes to the fat layer, then it enters into the muscle, and then it enters into the coelom, which is the empty space of our body. Then after going some part, it hits the outer wall of the uterus, which is the womb, and then it penetrates to the wall of the uterus. Then it goes to the amniotic fluid. Then it penetrates to the through the baby. Then it goes out of the baby and goes to all of these barriers, and eventually can get reflected off the what?
Backbone.
Of the backbone boundary. And when the reflection will come back, it will also have to go through all of these medium changes. Now, whenever this thing will happen, we can ultimately get this reflection available over here after a small bit of time, because this entire thing is practically a mixture of solid and liquid medium. There is not much of a medium, but it's a mixture medium. It's not a single medium. That's what is really important for you to understand. Not like sea, ocean, water. There is solid muscles. There is empty space. There can be some liquid as well. So through this medium, this reflection, this ultrasound pulse will go through, get reflected off the backbone, and be received onto the transceiver after a while. The machine is smart enough, or it is taught well enough, that by analyzing that reflection type, it will be able to give us information accurately that where that baby's skins are. So it will be able to detect where the entry skin of the baby is and where is the exit skin of the baby. So it will know 2 specific points of the baby. For one ultrasound pulse, it will know 2 specific points. Do you understand why 2? Because the ultrasound pulse is going through the baby and eventually coming out. So it can do its own calculation and find out where those 2 skin points are. বুঝা যাচ্ছে?
Skin points বলতে কি বোঝাচ্ছে?
মানে হচ্ছে যে বোঝাচ্ছে যে this is one skin point through which the ultrasound pulse was entering, and this is another skin location in which the ultrasound pulse was exiting. So these are the 2 skin points of the patient's body, of the kid's body, which the machine can know. So these are coordinates, let's say. Okay, so we are not going to do this only once. This transceiver actually makes hundreds and thousands, depending on the design, thousands of ultrasound pulses, and it detects those information. It collects a lot of coordinate data every second, and whenever we do this scan over the entire part from the very left side to the very right side of the patient's body, we can pretty much get all of the coordinate data for the baby. And that data, when in a computer screen, is converted into black and white picture, and that gives us the 2-dimensional image of the orientation of the baby. So it's very much like the fishes. Remember those fishes, that whenever the fishes were present, we got some flashy or discontinuous reflections. Here we're also going to have that, but this analysis is going to be far too more precise compared to the oceanic fish capturing ships. Do I make sense?
Yes, sir.
Yes, sir.
বুঝা গেছে?
Yes.
Now what is the magic that happens inside the device to calculate out these locations? I'm not getting into that technical jibber, but we need you to understand that it is possible to distinguish those 2 reflection time frames. Using a good enough sensitive transceiver, this device can distinguish that which of the reflection occurred from the first surface of the baby and which of the reflection occurred from the second surface of the baby. The device can find and distinguish those 2 points, which is the basis of the ultraprenatal scanning. So that's that part. This is also uses of ultrasound. Why am I teaching uses of ultrasound right now? Because we are in the sound chapter, and I did not teach you this earlier. It's a good thing that I have access to the notes. I actually remember stuff that I tend to forget. Beyond this point, we have this. Yes. No, we don't have this. Beyond this point, I think we have this. Let's have a read of this one. I'm not going to get into this experiment today because we passed your starting time. but I will cover this part that I have already at hand. So let's have a look at this part at least. So have a read over here and see if it makes sense. এটা পড়ো কি লেখা আছে এখানে আচ্ছা আমি পড়ে দিচ্ছি using the probe ultrasound pulses are sent aiming at the backbone which works as final reflection surface. Whenever ultrasound pulses undergo medium change, reflection is sent back to the probe. Medium changes such as skin into fat into muscle into worm wall into amniotic fluid into fetus into backbone and then backwards again. So it says the more dense the reflection surface, the stronger is the level is the reflection. The far away that boundary is, the thicker is that reflection medium. হ্যাঁ মানে যে রিফ্লেকশনটা যত দূরে থেকে হবে সেই রিফ্লেকশনটা ব্রিজ করতে সময় লাগবে বেশি. So you can essentially determine that which reflection happens earlier and which reflection happens a bit later. That difference of the time information tells you where those two boundaries are located. So একটা সিঙ্গেল বাউন্ডারি যদি অনেক মোটা হয় তাহলে তার স্টার্ট পয়েন্টের রিফ্লেকশনের থেকে সেকেন্ড পয়েন্টের রিফ্লেকশনের গ্যাপ হবে অনেক বড়. For example, if a baby is really overgrown inside a womb, then that baby's thickness would be represented as a much bigger compared to a regular size baby, and vice versa. So it's the time information which helps us to determine the thickness of that medium. আচ্ছা
কি করলে বেশি টাইম লাগবে না রিফ্লেকশনটা আসতে?
মোটা হলে রিফ্লেকশনটা বেশি সময় লাগবে আর ছোট হলে those two reflections would be really close to each other because the bigger the object is, the sound has to travel longer distance for the second surface, that is.
Yes, I understand.
Sure. So it goes further. It is then thicker the reflection medium. The probe precisely detects the reflection intensity and time gap. Then the computer compiles the data in a pixelated background, black and white. Is a pixelated shadow image. This is the ultrasound scanning. বুঝা গেছে কি প্রসেসটা?
Yes, sir.
Sir.
Okay. ঠিক আছে, I really appreciate your understanding. পলাবান তোমরা আমি তোমাদের একটু নোটস দিয়ে দিব। সো তোমাদের দুটো নোটস দিব, একটা দিব জুবাইর, একটা দিব নাজিফের। দুটো নোটস অনেক ভালো মতন লেখা আছে। So I would like you to read through them, compare the stuff that which is missing where and which is additional where. They might not be as well identical because I'm a human being and মানুষ মাত্রই ভুল, man is mortal. So I want you to work through it. Thank you for today's class. I'm going to stop the recording. Some of you had some additional questions that you wanted to ask me in the class. You can ask me those questions, but I'll take a small break.